always doing that. I'm Edward. I'm going to be giving the talk today.
You put the brown cord.
I have been a member of Less Wrong kind of for 4.5 years. I guess I'm mostly a lurker, but I've been interested in AI and AI research and AI risk prevention for years, pretty much the whole time. And I've done a lot of research over the past few years, and I think what I have for you today will be pretty interesting. So, without further ado, let's get started. So the ideas that I'm going to go over in this talk are the nature of human intelligence, a refutation of something called Pascal's mugging, and the economics of artificial general intelligence and hard AI takeoff. So, just as a precursor, how familiar are you guys on this kind of stuff? Anybody want to share some Actually, you kind of gave a good indication in your introductions. You seem like you know about some of these, but I'm going to go over some of the topics that are the background for this, just in case anybody's a little unclear. So before I do that, one note about some of the terms I'm going to be using. A lot of these terms have been defined, but it's not exactly clear what those definitions mean or how they relate to the real world. There are a lot of things like even intelligence that you can sort of point to, but you don't really know how it works. I just want to caution that these kinds of things are a little black box. They're a little black boxy to think about, and you should be very careful when you're considering them and when you're using them, because it is very easy to confuse yourself and trip up on even the most basic things when thinking about them. So the kinds of terms, there's intelligence. There's also artificial general intelligence. I know I've already used that, but even that is a little confusing. Sometimes it refers to human level intelligence, which is also a little confusing itself. These things are unclear. We're not sure what to point to and say this is or isn't it. For artificial general intelligence, you might say, okay, chess AI that only explores chess is not a general intelligence, and that's a reasonable claim. There's IQ, which is not necessarily it's a metric we have which maybe isn't as immediately relatable, or you can't think about it you might not be able to use it to make claims about other events that might occur. But just all of these are like that. So optimization power, sometimes used as a replacement for general intelligence or intelligence. Utility is a pretty important word, which is very, I consider this to be a little hazardous to use. And qualitative, which is usually a distinction maybe in intelligences between something that goes really fast and something that is completely new and nuanced and something in a way you can't even compare metrically. So yeah, just cautionary note. Be careful around these terms. So I guess we'll start with information about human intelligence and animal intelligence. So IQ is the most relatable, most, I guess, understood, most real-world metric that we have when we think about intelligence. Maybe it's not the thing we point to all the time, but it is, it's the intelligence quotient. It's the number we picked for intelligence. People take tests, they get a number, and there's a distribution of intelligence, of rating scores on this test. This may not be a very straightforward indication of intelligence. You might not call somebody with IQ 200 like twice as smart as somebody else. You might not call somebody with IQ 50 half as smart, or 0. But it does seem like it's definitely correlated with something that we call intelligence. So it's useful in some circumstances, but it might not be useful in all circumstances. So let's see. Let's start with some specs on the human brain and some information about how the central nervous system, or in this case, the brain of the human, works. So there are around 100 billion neurons in the human brain. Or the brain is composed of neurons and synapses. There's also some other things there, and the process of intelligence is more than just those things, more than just those two items. But there's about 100 billion neurons. It's actually closer to 86. And about, yeah, 86 billion. And about 100 trillion synapses. So the synapses outweigh, well, maybe not outweigh, but outnumber the number of neurons about 1,000-fold. It's a pretty good metric, or heuristic. So the cool thing about this is that is a lot compared to, well, it's a lot compared to the neural networks that we have on computers today, for example. Some interesting things about central nervous systems in animals are that the number of neurons, the number of synapses, weight, and volume, and even energy use of central nervous systems in many animals are exceeding, like, all scale pretty much directly proportionally to each other. There is some tolerance you have to allow, but even from something like a mouse or an insect all the way up to a human, and even beyond a little bit, you have a certain scale. You have these metrics which scale in direct proportion to each other. So it looks like something's going on there. It seems like you might be able to break it down a little bit to infer something from that. So as a thought experiment, we're...
Just to understand your last point, are you saying there's a correlation between the synaptic density and the level of intelligence of the organism?
Not exactly. What I'm saying is that number of synapses, number of neurons, overall in the entire brain, number, like the actual volume of it, the actual weight of it, are numbers that for each brain are in direct proportion, like as you look at them. So it's not any indication about like which organisms are smarter. It's actually an indication about how intelligence works in organisms.
Also, you're saying that like this thousandfold difference in the number of synapses in the neuron tends to
stay the
across- right,
yes,
right, okay.
exactly.
And the number of neurons per unit volume is also the same.
Exactly. And the amount of energy used per unit volume, or per unit weight, or per neuron, or per synapse. So now we're getting into the history of human intelligence and the origin of it. So humans are pretty smart. I mean, we're all here today talking in this crazy symbolic language. When you look at other animals, they look completely different from us. They have no tools. Well, some of them have tools. But they have almost none of the inventions that we have today. What happens? What's different? Why are we so much different from other animals? What's the secret behind our success? So I want to imagine a thought experiment right now. Suppose you take a modern human baby and a human baby from, say, 100,000 BC, or 100,000 years ago, and you swap them, like changelings. What would happen? What happens to the baby who has today's DNA? It grows up 100,000 years ago. What happens to the baby from 100,000 years ago that grows up today? Well, I have a hypothesis, and that hypothesis is what I think would happen is that the baby sent to 100,000 BC would grow up looking like, well, maybe not looking like, but doing the same things as everybody else around them. Maybe they would be segregated, but ignoring that, they would grow up learning the same kinds of things as the people around them did in 100,000 BC. So what this means is, in 100,000 BC, there were surprisingly few inventions. Like, basically, math didn't exist. Counting systems didn't exist. I mean, there was probably some counting systems. Language was very limited. There wasn't even pottery back then. Like, things that you assume, like, even the most basic, like, tribes of humans doing, that some of that stuff didn't exist. A lot of it didn't exist. In fact, if you look at them, they kind of look more similar to, say, some other animals like apes do than they do to us. Cave people, well, maybe they didn't live in caves. So this is the hypothesis that the information is the crucial part of this intelligence, of what we see them being able to do. That the fact that they grow up in, that the fact that people grow up in today's society allows them to be much smarter than they would be otherwise. That if you took somebody from even today's society and you let them grow up in isolation with no information around them, that they would do incredibly poorly, to the point of not even developing language, to the point of not being relatable on almost any level. So this is the communication hypothesis, that there is a slow buildup of information quality and language and communication over a very, very long period of time that results in the human intelligence that we see today. That we started very stupid, and over a very long period of time, we gradually got smarter and smarter, trading better and better information with each other, until we invented society, civilization. So from this, you might imagine that certain technological progress with respect to communication resulted in particular advancements in humanity. And you might be right, because pretty much immediately after writing was invented, civilization basically just sprang up immediately. And writing was invented, maybe art was definitely invented like over 50,000 years ago, but writing was invented in like 10,000, 15,000 BC, and civilization started around then too.
What is your evidence for that statement?
I'll get to that at the end. Yeah, I'm going to be saying a few things for which I can't exactly just stop and give evidence for immediately. So there's writing, there's the printing press, which resulted in education being given to the masses, the ability to read and write, propagating throughout the layers of society, the cliques. And there's mail, the phone, TV, internet. All of these are like huge civilization-changing inventions, which like changed the very way people lived their lives. Even social media platforms, not even something that was built, although the internet also kind of wasn't something that was built. Social media platforms are like single sites that are capable of this kind of change. So it seems inline, but it's not exactly, it's not maybe completely complete evidence for it. It's not a proof by any means. But enough about that for now. We're we're going to get into some terms here. So if you've already heard these terms, don't worry. They're important. And you should allow everybody else a chance to learn them too. So what is Occam's razor? You want to tell me what Occam's razor is?
The hypothesis, among hypotheses to explain a phenomenon, the hypothesis that is the simplest that can explain it is to be preferred.
Right, exactly.
It's a vague statement of Solomon priors.
Yeah. Yeah, it is very related to Solomonov priors. So yeah, Occam's razor, pretty interesting tidbit. Has resulted in, usually used as an argument in as like almost a rejection of completely absurd claims and like complex scenarios when there is a simpler alternative. Yeah. So Pascal's wager. Does anybody know what that means? You want to go?
Pascal's wager.
Pascal's
The
wager.
mugging? The wager?
No, just Pascal's wager. We'll get to Pascal's mugging.
It means that you should believe in God because the payoff of even like a bet with small probability is so high.
Yeah. So like, if you believe in God, go to heaven. If you don't believe in God, you go to hell. If God doesn't exist, nothing happens. But like, if He does, you probably should have believed in God. And if there's any chance of God existing, well, then you better have believed in God because expected payoff, right? So what is Pascal's mugging? So this is a pretty well-known post on Less Wrong. It's not as old as time itself anymore. It's a more recent thing. So usually the phrase goes, the way it's stated is, give me $5 or I'll use my magic powers from outside the Matrix to run a Turing machine that simulates and kills Graham's number of people. It's a bit of an extreme statement, but that is how it works. So what are some ways to combat this? What do you, yeah?
The argument that the mugger is making is the expected value to you of you giving into his demands is greater than the expected value of you not doing so.
Exactly.
But some of the original objections to Pascal's wager are there's the Christian God, but I could imagine all kinds of other gods that would throw me into hell if I believed in the Christian God, but would not throw me into hell if I didn't believe in any God. And so the statement that it's absolutely preferred to believe in God, that is even a positive payoff, is just uncertain.
Yeah. So let's get to one of the main points, one of the crucial new things. What I give to you today is Pascal's taser. Don't mind me, bro. It is so here's how it works. Suppose somebody comes up to you and says some words to you, shakes his fist, says something about like Graham's number, you're confused. You're like, what's going on? So essentially how it goes is that there's this idea of having somebody specify utility at you, like, here, I'll just give you 100,000 utils, and it just doesn't make any sense from the onset. Like, somebody walks up to you and gives you a scenario, mentions a scenario, like, or it exists as a possibility. Like, that's not the way human brains really work. Like, we are reinforcement agents. You can't just specify infinite value. You can't just specify extremely large value. Even if you do, it doesn't matter. Language is a communication platform, right? So if you're going to tell me something, you're telling me like, okay, I'll do this. You're referencing things that I can deal with in the real world. You use language to set up possible trades, but you're referencing those trades. You're referencing trades that the other person can think about, can imagine happening. And something like this, well, it's not a reasonable trade. It's the specification itself is essentially nonsense. Something he's like, the mugger is saying words to you that don't relate to an actual scenario that makes any sense to how you do trades, the way you decide things in the first place. Certainly, expected payoff is a useful tool in certain circumstances for gaining resources and for making better trades. But in this one, it seems like there's something weird going on. Like he's just trying to break your system by saying words, right? I might get back to that in a bit, but we're going to change gears a little bit and move back to AI. But I guess before I do, any immediate questions?
Your defense against Pascal's plugging is literally humans cannot deal with large numbers.
Not exactly. It's more that utility specification itself is not an interesting problem. Like, saying any kind of numbers is just a means of setting up a trade.
So your defense works even if I change Graham's number to 10 to the 50?
Sure.
So I think one way I can interpret what you're saying is if a guy comes up to you and says, I will give you negative 10 gajillion utility if you don't do what I want, and that doesn't make sense. But it seems that I could still turn that into something that would make sense. Like, I will inject you with chemicals that will prevent you from dying, and then I will torture you for 100 billion years. I think there is a valid objection to be made, but I don't think the one you're making is
I mean,
essentially the right one.
you're still specifying something which doesn't exactly make sense. You can say something, but that doesn't mean that it actually has a likelihood or a prior that is like with that I have any prior for it. It doesn't mean I have to set up or consider the scenario. I don't have to execute your code. You mentioned something. You're just trying to communicate something to me.
Give me $5 or I will shoot you. Well,
Sure, in that case, they're gonna shoot you. They have a gun out.
Right, but it seems to me that your objection is just as valid against that scenario.
No, because in that scenario, they're like,
The distinction.
the distinction is that they are like they're taking a scenario you already had a prior for and changing it.
Suppose I'm from the year 1000 and I've never seen a gun.
Okay. I mean, then you don't know what's going on. How are you going to deal with it?
Well, that's moving for you.
If you literally don't know what a gun is, how do you use if they tell you what guns are and how they work, show you how they work, then sure, maybe you think, okay, it seems kind of bad. Don't want that to happen to me. What's up?
So it's definitely correct that like humans are really bad at reasoning through these kinds of things because they're really unfamiliar with them. But like, what do you think like a hypothetical like perfectly rational agent should do in these situations?
This isn't about being bad at reasoning. This is about language as a means of communication, not a means of evaluating things. This is about, like, it's not humans being bad at interaction, it's humans receiving information and not being able, like, the information isn't interesting in the first place. It's nonsense.
I'm not precise. I might just as well claim that, well, I'm not interested in being shot, so your threat doesn't matter to me.
You're not interested in being short? Shot? Sure.
Some people do that.
But like being shot is not a nonsense thing. You're communicating about something that they know
No,
about.
excuse me, you're just asserting this is nonsense. This is not nonsense without Says who?
In one circumstance, somebody is mentioning a scenario which is like directly affecting your utils. They're setting up something which you don't have any priors for. And in the other circumstance, you understand things. They have a gun. You know what that looks like. You're already worried about that. And you understand what it means.
Is your distinction here that you're hearing something being threatened? Let's say you're hearing a threat,
Sure.
and it's that threat. The words used to describe the threat mean nothing. Like I'm going to, put you on the planet Gorgon or something like that.
Yeah.
Versus another thing that you perfectly well understand is like we're going to shoot you up to Mars.
Yeah. It's like they're just mentioning gobbledygook.
Okay, so it's not, because the second one, you can evaluate that. How likely is that? I understand what that means, shooting to Mars,
Yeah.
but shooting me to Gorgon, I mean, I don't even know where that is.
Yeah, exactly.
Okay, so the point is that, like, I guess you can't necessarily just look at the words to do your evaluation.
Exactly.
Because depending on how threatening the guy looked, you can perceive a threat, even if you don't know the actual words that, the meaning of the words that are being said.
Mm-hmm.
Or you could understand the meaning of the words very well, I guess, and, think that it's BS because you don't believe the guy. But
Exactly.
there's, I guess, to your point about the words not being sufficient it's sufficient to communicate something, but it's not sufficient to give you all the info you need to evaluate the proposition.
Right. You're sending information to them. You're setting up a trade by indicating certain paths, but you can't indicate a path which doesn't make any sense to begin with.
But we are all discussing this scenario as if we understand perfectly well what it means. So why do you say it's nonsensical?
Well, imagine.
There could be something that is nonsensical.
I can certainly threaten to do a nonsensical thing, but I don't think that's what's under discussion here in Pascal's mugging.
My confusion is that what I'm hearing is that you're using Pascal's mugging to say something about the limits of human language, but it could also just say something about the limits of the utility functions that we use. Like maybe we should cut our utility functions off at a certain point, or a certain, minuscule probability we should ignore, or that just multiplying probability times outcome is not.
So that's the thing. I don't think utility is an interesting way to go about this, and I think it clouds what's actually going on. Utility itself is not. It's not exactly related. I mean, you can mention it. You can mention utility, but like, what does that actually mean? The way human brains work, they have reinforcement systems, dopamine, serotonin, which lead you to learn things, and there are probably other systems. They lead you to make decisions, but none of that, you can't actually know what your utility function is. Like, it's absurdly complex, if it even is a utility function, even if it's even like closed under that John von Neumann's utility functions. Yeah, like you might initially think, oh, what if we just have a number? But like, it's not a number. That's not how it works.
Wait, what? Isn't under von Neumann like the axioms it is a number?
Sure, for utility,
Okay.
but for the brain, it's not a number.
Why should I care about what brains do? I mean, like, sure, we are operating on brains right now.
Okay.
Right. Okay. So you're necessarily making a very strong claim about the number of minds which are possible a priori by saying that we care about brains, okay, and not about like all the other possible types of intelligence. Okay, so you're asserting by fiat essentially so far that the only form of intelligence possible is implementable in a brain.
No, not really.
Okay, then why care about brains?
It's pretty important to this.
Yeah.
Okay, let me move on.
Yeah. Okay.
Okay, we can go over this more at the end, but So yeah, what artificial general intelligence does exist right now? What kinds of general intelligence exist? So what does the term AGI mean? It's one of those black box terms, but we're gonna start with formal AGI, mathematical AGI, universally intelligent agents. So show of hands, how many people know about AIXI? About half the people here. Yeah, so AIXI is a formal definition of a universally intelligent agent. It happens to be incomputable, but theoretically it would do the optimal thing given some data and a particular heuristic. There's also something called AIXITL, which is the time-space bounded version of AIXI. So now it is no longer incomputable, but it is infeasible. But for those of you who don't know about AIXI, I'm going to go over a little about how it works. Essentially, the definition is treat the inputs and outputs of the intelligence program as the inputs and outputs of a function, which we will call the world or the universe. And try all possible, or look at what is returned, try to figure out what the function is by taking the list of previous inputs and outputs to the world and using Solomonov induction to figure out the closest thing that you have to the correct, the best possible guess for what the world really is. And then of those worlds, look at all possible inputs you can give to those worlds, and then all possible outputs, such that and then look for those outputs for the best possible result, essentially. There's a bit more involved with looking at its own actions in the future, but we'll assume that's most of it for now. You can see how that's incomputable. How many of you know what Solomonov induction is? About the same number of people. So Solomonov induction is how it works is you run all Turing machines slowly, or you just run all Turing machines and take the ones which halt and give you answers for a set of inputs and match up on all the correct inputs and outputs. And you weight them by how long the program length is, and you take the average result and you output that. It's your best guess for the next output of a function. It's also incomputable because it waits for programs to halt. But you can run it slowly, and then it is merely infeasible. AIXITL is an infeasible version of AIXI, which is actually theoretically the best possible algorithm for any given problem times a certain constant, where that constant is 2 to the power of the length of the best possible program, or the fastest program, for solving that problem.
Okay.
So it has equivalence-ish runtime complexity. So there's also, if you're worried about all of these being infeasible, there's also the Monte Carlo approximation of AIXITL. Monte Carlo approximations are typically giving a bunch of random inputs to something and taking the average of the results. So like the Monte Carlo approximation of pi is to put a bunch of dots on a square and check how many of them fall within a circle, or it involves that. The Monte Carlo approximation of AIXITL is actually not infeasible for some things. It can handle pretty simple game theoretic scenarios very well. But if you scale up the number of inputs, more than like 1 or 2, maybe up to 10 inputs, it starts having a lot of trouble. And then there are Gödel machines, which are actually a little bit better than AXI. They're still contained kind of within AXI, because like AXI will find all possible Gödel machine programs. But Gödel machines are AXI if it can prove things about its own search space and its own program. And there's still a few kinks mathematically to be worked out among them. There haven't been any Gödel machines created yet. But if they were, it is at least somewhat likely that they would be infeasible. It's possible there would be a Monte Carlo approximation of Gödel machines that would not be infeasible for some problems. So let's move on to neural networks. The current best AI in the field, the best general intelligence that we have. Neural networks are essentially also an approximation of AXI, though the heuristics may skew the program space that they look at, or their weightings for it. So, how many of you know what a neural network is? Everybody raise your hands. Okay, most everybody raise your hands. Neural networks are based off of the human brain, or brains in general, I guess. And there have been recent advances in neural networks in performance and in scale, but mostly in scale, I think, such that we now have bigger and bigger neural networks trained to do more and more complex things on GPUs and servers and server farms, and they're getting pretty big. But how big are they getting? Well, right now, yes?
What is a neural net?
What is a neural net? That's a good point. So a neural net is essentially, if you know how the human brain is composed of neurons and synapses, well, in a neural net, this is nodes and weights, analogously at least. Neural nets look like a graph where the points are the nodes and the weights are the edges are the weights. The data is actually mostly contained in the weights because the weights far outnumber the nodes, and there are even data structures where the nodes are not even part of the data structure. It's merely the organization that shows, but we're getting off track. They look like graphs from what you'd expect from like graph theory.
They don't necessarily have any of the same architecture that the actual neurons do. The constants we were talking about earlier.
Right. So there may be some differences to actual brains, and they might be very big. But essentially how neural networks work are they have a bunch of inputs, and they have some outputs, and they have some layers in between. And so the inputs are sometimes called an input layer. The outputs are sometimes called an output layer. And then there are a bunch of hidden layers in between, which in synapses that go weights that go from the input layer to each layer and between each layer to the next one. Usually, mostly like just from one layer to the next. All the weights for each layer just go to the next one. So it looks kind of like everything. So the most simple form of this is a feed-forward network where there are no a feed-forward neural network where there are no cycles where a neuron can have a weight that points to a neuron which points back to itself, or eventually a path back to itself from any neuron to any neuron to the same neuron. So feed-forward neural network looks like that. I guess I could draw. We don't really have the space to draw.
So you're saying there's no feedback?
Yeah, so a feed-forward neural network has no feedback. There is a thing called backpropagation, though, and that's actually how the neural network learns, and in fact how all neural networks learn, I'm pretty sure. So backpropagation is the means of which neural networks learn, and the way it works is you take the final layer, what it gives you, and you say, you look at what you wanted to see, and you tell the neural network, okay, here are the differences between what you gave me and what I wanted to see. Make some changes. You were clearly wrong. And the neural network takes those, what it like gave you, and it propagates that back and looks at what each node fired with, and how much each weight was a part of that final error. And it propagates back and changes all the weights a little bit, and becomes a little bit better at, hopefully, at predicting or being useful for what you want. The usual simple examples of this are perceptrons, but I'm not going to get into that right now. So, point is, neural networks are based on human brains. And let's compare some of the specs. How big can they get? Well, currently, if you buy a GPU and you want to hack on a neural network, make your own and train it to do something, you can usually manage somewhere around 500 million weights or synapses in a single neural network. Sometimes it's less, sometimes it's more. Depends on what kind of graphics card you have. Graphics cards, you might get one that has like 4 gigabytes of memory. That's a little high end, but it's probably not that bad. And yeah, each weight takes up about 4 bytes of memory. Sometimes there's double precision, and I'm not sure if state-of-the-art neural network software defaults to double precision floats. But each weight is like a real value. It's not a 1 or a 0. It's or it's not an integer either. It's a real value, or a floating point value. It's an approximation of a real value. In fact, if it was a real value, you would be able to implement like hypercomputers out of neural nets. But I'm not going to get into that. So 500 billion, or wait, 500 million? 500 million weights. That's a lot. That's a lot, right? You'd imagine that's...
Compared to the 100 trillion.
Right, so the human brain has 100 trillion synapses, which are somewhat analogous to weights. They actually might be better than weights. They're usually thought of to be strictly better, equal to or strictly better than weights.
Just a point of order is that my battery is running out, so if someone can take over the video duty, that would be...
Sure. Does somebody else have a phone?
I can take it.
Cool.
Thanks.
Yeah, everybody has a phone.
Neurons, are they like a universal combination?
Yeah, so they're an approximation of AXI, and they're currently the best artificial intelligence that we have. They have the broadest application. They're used for
Just related to that, so in neural networks, I think people are excited. In popular press, people get excited because they think they're like brains. But there's statistical learning methods that are just usually models of other statistical learning methods.
Right.
They're really cool. I guess what I don't know about is when you say it's an approximation of AIXI, are there statistical learning methods that are not approximations of AIXI?
Not exactly.
No.
Kind of, yeah.
All reinforcement languages are approximations.
Pretty much, yeah.
So the question is, why do we care about them?
Yeah. They may. So I think it's a little bit of a. I don't know. It's a little bit of a kind of like white sheet, a kind of no answer. If somebody says, "Oh, look, neural networks are not brains," okay, but they look pretty similar, and you might be able to reason and look at both of them and make some assumptions, test some things. Sure, they're not brains, but they might be, for example, asymptotically the same. So
Given that they don't respect any of the architectural or energy constraints that, you know, we were talking about earlier with brains, what makes us think we can learn anything about brains from neural networks?
what do you mean by they don't respect architectural? What was that about?
Okay, well, what I was trying to ask earlier, when you were talking about neural networks and nodes and things, and the graph structure, I was thinking back earlier to the 1,000 synapses per neuron, and thinking of the synapses as if they were the edges, and the neurons if they were the nodes.
Yeah.
And wondering if we have any data on whether neural networks have the same sort of ratios, like that we were talking about is conserved among different brains.
Yeah, so neural networks are very much more understood. You can actually change the kind of ratios. If you have, for example, a 2-layer neural network where you have just the inputs and just the outputs, there's the input and output layers, and each layer is like the same size and it's really big. How many weights is that? If you have like n inputs and m outputs. It turns out the number of weights is n times m. So potentially it could grow, the number of weights could grow much higher than the number of individual nodes. So
I don't have any more storage on my
does
Okay,
anybody
mine is
else?
still functioning, but I think it might die any minute.
Anybody else?
I'm audio recording you, so we just won't have video.
Sure, that's probably fine. Okay, so yeah, human intelligence. So yeah, 100 trillion synapses. That's a lot. How big is that on a computer? I assume some of you are familiar with storage costs for computing. So if we assume single precision floats, and we take the number of synapses from the human brain, and we try to store this as data, 100 trillion times 4 bytes per synapse, or weight, is about 400 terabytes of information. That's a lot. 400 terabytes. And actually, the important part of this isn't how much memory that it takes up, and not even how much performance it takes, because performance is actually a little better than memory in computers, but or less of a bottleneck. But the actual bottleneck here is the refresh rate of the memory, the throughput of the system. In a human brain, on average, to overall, around 100 trillion synapses are being fired a second. And if you try to update all of that, if you try to update all of the information or even use it, you have to take it into memory and then do something with it. And in order to do that, if you look at the throughput, for example, of hard disk drives, which are some of the cheapest memory around, what is the throughput of a hard disk drive? Anybody want to yell it out, like a typical hard disk drive?
100 megabits per second.
100 megabits?
Yeah.
Okay, 100 megabits per second. And the total storage of the disk drive is how much?
2 terabytes.
2 terabytes. Yeah, so it's a lot of storage, but very comparatively little throughput. The thing that you want here is about as much throughput per second as the entire storage of the device. So you want 400 terabytes of throughput, or terabits per second of throughput. Terabytes per second. So how do you do that? Well, actually, we have this really cool thing called RAM, which has incredibly high throughput, and it's used in computers today. Only problem is RAM is a little more expensive than hard disk drives. And you might be thinking, well, wait a second, we got SSDs. Yeah, unfortunately, SSDs have pretty low throughput too, compared to RAM. It might be higher than hard disk drives, but usually only by a factor of 10-ish. Whereas RAM, on the other hand, can be refreshed several times a second. And you essentially need to buy RAM just for the throughput, though it will satisfy your memory constraints. So how much RAM are we talking? What is a typical RAM stick that you can buy? 8 gigabytes? For how much?
$40 to $100 depending.
Yeah, so we'll call it, $50 for, I think that's a little high, but $50 for 8 gigabytes of RAM, a little reasonable. How many of those do we need for 400 terabytes of throughput? Or just space, really, because you need all of that space. You need all
50,000,
50,000?
is that right? From giga to
50,000 is about 1,000.
Is 50, then 8 terabytes is 50,000, and then 40 terabytes would be 250,000, and 400 terabytes would be 2.5 million.
$2.5 million.
No, 3.5 million
of those things, so times 50.
Wow, $2.5 million. That's a lot. That is a lot.
At the scale of a large company,
It's true. It's not that much. Yeah.
There's some probability that at the next meetup there will be somebody in the room who could fund that out of his pocket change.
Maybe, yeah. But yeah, that is. It seems a little hard to deal with. Like if you're talking about making a human intelligence on a computer, somebody's like, "Oh, I'm gonna build a human level AI out of a neural net." Well, it's a little difficult, right? Even if, and this is assuming that neural nets have the same kind of performance at that scale. Little up for grabs. Probably not the case right now. But yeah, several $1 million for a human level intellect. Just human level. You might be able to modify it, but it's taking up those kind of resources just to learn. And just to learn like at around the same speed that a human does. At least if it works that way. It might not. So let's move on a little bit. In fact, I think possibly one of the biggest bottlenecks here, that is a bottleneck, by the way, but another bottleneck is the problem of training this neural net, because like human brains are trained to do a bunch of different things, an unbelievable number of different things. Your entire life has been training. You've been training all this time, and for what?
Cheese and video games.
Yeah. So yeah, there's the problem of training. How are you going to train a neural net to do a bunch of different things at once? Because you need to train it to do a bunch of different things at once. If you want it to discover things that it can use on all those different things, you need to train it in a better way. But we'll get into that. That is another bottleneck. Both of these are bottlenecks. So hard AI takeoff. Yeah, we're getting into the crux of the matter here. Hard AI takeoff. What do you guys know about hard AI takeoff? Anybody? Also known as FOOM.
If you make a sufficiently intelligent general intelligence that can modify itself, it could increase its general intelligence at a rate that would exponentially explode.
Yeah, exactly. So a hard AI takeoff refers to the scenario in which a single AI project rapidly self-improves on a time scale of a few years or even days. So, what do you think when you hear that? Wow, pretty scary, huh? Yeah, the singularity sounds pretty similar. Yeah, my initial reaction to this is it sounds too hand wavy, to be honest. It's mentioning these like black box things, intelligence, it self-modifies. Like, okay, sure, but like, how does that work, right? So I initially want to reject it just because it's so informally stated. It doesn't refer to things that you can work with. You know, it's hand wavy. It's magical. But we're gonna assume that we got some valid things here. We're gonna look into it. Okay, so what are the central arguments to hard AI takeoff or FOOM? What is the first one? Well, humans are kind of dumb. I mean, we have these biases and fallacies. We make all these wrong judgments. We make mistakes. We go to sleep. Like, I mean, if you're doing it right, don't sleep, right? You should always be online.
Why would such a guy, want to keep us around?
Yeah. Humans are pretty dumb. So clearly you can do better, right? With computers. Computers are really fast. They are really good at math, which is like some of the most intelligent stuff ever. It's crucial to doing tons of engineering. They run on chips, which are not prone to error as humans are. Their chips have like amazing error tolerances, or rather, they have amazingly few errors. They have access to ridiculous amounts of data. Like the throughput for a computer is just far higher than that of a human, right? Like you talk to a human, you're saying some words, and you're saying words at like 200, 150 words a minute, right?
Is words really the right metric? Why not like video, audio, plus, I don't know, whatever this thing is?
The nose. Yeah.
Yeah.
I don't know what that is.
What would that throughput of that be compared to?
Good question.
Yeah.
And yeah, that's a good point.
Yeah. Words doesn't seem like the right level of.
Yeah.
Yeah.
And computers are also like discrete. They're already hooked into the math. Like they can immediately just run programs and get the responses of those. But these two initial ideas are a little hand wavy, right? Because like when you actually look at it, humans are the smartest animal in the world, and we do incredibly complex things all the time that computers still can't do, of such breadth that it's pretty ridiculous. And even for all that amazing speed, computers have some problems. Like, oh yeah, right. The throughput for humans is actually a little higher, like
A little?
a little higher, yeah. Maybe several megabits a second, maybe even gigabits. Who knows? We have incredibly good hardware, but computer transistors operate at such higher speeds than neurons, right? Like, you take a transistor, it's switching at like gigahertz. Sometimes, I mean, if you're really good, maybe it'll become terahertz in the future. Who knows, right? But it's currently gigahertz. So that's really fast. You know how fast neurons like fire? Maximum around like 1,000 times a second, something like that. It's pretty slow compared to transistors.
Isn't it something like a little less than 100 milliseconds?
Yeah.
It's more like kilohertz.
Instead of gigahertz, yeah, you have a factor of 1,000,000 of difference. Like, that's ridiculous. So clearly computers are like really fast. But at the same time, the power of the human brain, again, when we made the comparison, is actually huge. It's ridiculous how huge it is. And maybe that will be surpassed in a few years. But the power of the human brain is not so easily washed away by the fact that our neurons don't switch that fast or fire that quickly. Yeah, what's up?
So what exactly are you trying to argue? Are you trying to argue that like maybe we should expect brains to be like fairly like optimal reasoners, or that we shouldn't expect to be able to make better AIs than humans on silicon, or like?
Yeah, I am in fact arguing that human brains do look pretty freaking good at intelligence and learning, I guess. it seems like they're very efficient. Yeah. But I mean, there's so many biases, right? Like we make so many mistakes. But what if those mistakes are just a very, just bumps in the road? What if they don't matter that much? What if they're like
That sounds very hand wavy.
constant slowdowns?
Sounds very hand wavy to me.
It does sound a little hand wavy.
Like
So, so let's go on a little bit. Do we want to take a break? Okay. So, so we were talking about central arguments for whom. So what if you make a super good learning algorithm? It's better than neural networks. Maybe it's neural networks with some cool extra things like being trained really well. This is part of the FOOM, like it's a kind of a central argument to FOOM. It's pretty much one of the assumptions. It seems like a prerequisite almost. And it has similar issues because it begs the question, well, where did you get that super good algorithm from? How did that happen? Why is it so good? Who made it? How did it come about? And why is it so much better than everything else? For example, suppose somebody made a girdle machine and it was suddenly amazingly good and it just like completely outclassed everything else. Well, what does that look like actually on the program, in the program itself? What does that look like from a computer science perspective even? It seems like that happening by default is incredibly unlikely, in the same sense that it's incredibly unlikely that you discover a sorting algorithm that works in square root time or linear. I know it's not exactly easy.
Actually,
What?
Oh no, you can find an element. You can like invert a function in square root time of like the input space in a quantum computer, which seems like, so if you have like a hash function,
Yeah.
you would think you have to evaluate the hash function on like every possible bit string to find the bit string that hashes to a given output, assuming your function is like non-invertible.
Okay, so
But you can just magically only evaluate square root of the number
Sure.
of bit strings on a quantum computer.
Does that mean that finding pre-images is as easy as finding collisions, or are quantum computers even better at finding collisions?
It's only a square root, so you only have key size.
No, they're even better at finding at inverting hash functions than just finding a collision.
okay, we're getting a little off topic
sorry.
here. Yes, it is related to algorithms, but
I mean,
there are things you can prove about algorithms. Yes. What?
so I mean, the usual argument is that let's say you get a system which is anywhere near human performance. Humans are really bad at programming. It's really hard for us to write an algorithm that actually is correct.
Okay.
We're pretty good about reasoning them. Everything we do to optimize neural nets and so on, the machine should be able to do at least as well as us. And then once you get it cranking on that, then it should outperform human developers trying to make better algorithms. So that's
Right. So an AI can make better AI. Exactly. But how does that work? How does it get better? I mean, certainly an AI could be smarter than other individual humans. So it would be better than other individual humans at, for example, writing AI. But what if writing better AI just doesn't matter that much? What if there's a theoretical maximum on the efficiency of a learning program? And what if that theoretical maximum in efficiency is asymptotic to human brains, for example? Asymptotically isomorphic, I guess. So
we're the best you can get, basically.
well, maybe not the best, but like the best at scale. Like you can get better algorithms. You can get better, like bigger instances, maybe. But like the efficiency that we run at is like as it scales, it grows the same. For example.
So it seems to me. So I really like the argument that like you know, humans are like the stupidest possible things that like could have made it to this level of civilization and like could have made it to like
Right.
this level of like ability to design better AIs, right?
Yeah.
So like it seems really surprising to me to somehow suggest that we've reached the optimum so quickly.
Right. So yeah, why are we so dumb?
Because evolution's not selecting for intelligence.
Exactly. So hardware wasn't almost any good. Our hardware, you're saying our hardware is bad, right?
Our hardware is constrained.
Constrained
Much
by our
more
skulls.
constrained, yes.
Yeah. So we're constrained to being individuals. Our intelligence cannot grow beyond our person, is the idea here.
Or our heads have to fit through birth canals.
Yeah.
Probably the more important.
Exactly. But there's the problem where you look at human groups and you see how they perform, and it seems like human groups do things a little smarter than individuals. So how much smarter is a group of humans than an individual human? Say 10 humans. How much smarter is 10 humans than one human?
In terms of what work they can accomplish? Or
Yeah, in terms of their ability. It's hard to quantify, right? Because we don't really know what intelligence is. It depends on the task.
It depends on how parallelizable the task is.
It depends on the criterion for what their opinion is. Like, if,
Yeah.
I mean,
It depends on a lot of things. But if they're like working together and doing a particular thing, for example, if they're employed at the same company, I know companies are a little inefficient at some things, but a startup of 10 people, how much better are they at like progressing or writing software than a startup with one person? Maybe not that much.
There actually is a measure kind of analogous to IQ for groups.
Okay.
And one of the discoveries, I think it was an MIT group, is that it's the more women there are in a group, the more intelligent it is.
Okay.
Because they work better together.
and if they found anything else that got published,
Well, there were a bunch of other things too.
That's
But
pretty
that was the dominant.
Plausible. And one of the sub-analyses of that at the MIT lab for selective intelligence is just that any social covariance, like the higher fraction of women are able to reason socially better, and so they can mediate a lot of those things better.
Yeah.
The surprising thing is that the average or maximum IQ of the group is not a very strong predictor of the total output of group intelligence.
Wow.
So like these like things that modulate the social network are.
Yeah. So now we're getting back to the communication hypothesis. The idea that communication between these individual agents results in each agent becoming more powerful over time, or smarter, and the agents as a whole becoming smarter. So, for example, with more communication between humans, you have bigger and bigger groups of humans that do more and more complex trades between themselves.
Is this like generally true? Like, could a group of humans beat the smartest computer at chess now? Like a sufficiently large group?
No. I'm pretty sure no.
So like in what cases is this actually true and not?
Uh,
What cases does intelligence scale and not scale groups?
I guess this mainly just looks to be true for like economic value, for example. Like, I don't know.
We could do the same thing for stocks, right? Like, could a group of humans replicate like derivative trading algorithms better than like the best algorithms?
Well, a group of humans can, for example, design their own algorithms and do better than other groups of humans. But yeah, this is more easily looked at in the past than in present times. Like tribes competing with each other or countries going to war. Yeah, it's along those lines. Anyway, so yeah, AI can scale so much, right? Like you can have a single AI that's 1,000 times as smart as a human. Shouldn't it then be incredibly better than other humans? Well, is it better than 1,000 humans? How do you measure it? What's 1,000 times smarter, right? It's uncertain at best. So if you take a neural network in particular and you scale it up 1,000x, what does the performance look like at that 1000x. Like 1,000 times the number of weights than a human. Well, there's an unfortunate thing that comes along with this. It might be easy to say, oh, it can copy itself a bunch of times, or download the internet, and or download Wikipedia, because that's much smaller, and just know everything in Wikipedia immediately, right? Doesn't take that much time to download Wikipedia. How big is it? How big is Wikipedia in like file size? A few gigabytes? 50 megabytes? What?
50 gigabytes.
Compressed it's
just
like
text.
500 gigs, and then uncompressed it's
500 gigs of
4
compressed
terabytes or
text.
something. It depends if you include pictures and videos.
But that can fit on a hard drive, right? Single hard drive. Seems pretty like, wow. If you had a hard drive in your memory and it just was all of Wikipedia, wouldn't you be like the smartest thing on earth? Well, not really, because you have to process it. You have to think about it. If you put a page of text in front of a human, they don't know everything that the text refers to immediately. They have to read it. And reading it isn't just a matter of moving your eyes over the page as quickly as possible. You have to think about the words and understand what's going on. So what's actually happening here is there is a limitation where humans have to, there's a limitation to understanding something, which might be like a form of learning where you consider things and you think about them. So you can't just download information. What about copies? Well, your copies have to run too, right? So they take up the same number of resources that you do. And if you have 10 copies, well, you're taking up 10 times as many resources. Can you hack those resources away from other people? Well, in order to do that, you have to be really good at hacking. Maybe in some circumstances, it's impossible to hack those resources away. There are no attacks that you can make on some sites that will actually perturb them.
Do you know how bad human security practice is?
Human security practice is really bad.
I'm not even kidding. Like if you knew,
It's pretty bad. I
it's
understand.
terrible.
It's completely terrible.
Like especially if you know about the internet, does that change your credence at all? About being like, it's not about hacking the strongest attacker. It's hacking every Dick, Jane, and Mary whose password is password.
Okay.
Okay.
Yeah, and that could be pretty bad.
Okay, gotcha.
But there are people who try to exploit those things already.
Yes.
And succeed.
And succeed, yeah.
But they're also limited by the same resource thing, and they don't spend all the time doing it. And they also pay a price for doing it.
There are probably some people who generally spend all their time doing it.
Yes. But it's much easier to trace.
Yeah. So.
Because like the number one thing which catches those people isn't like sophisticated security techniques. It's also operational security. Like they just don't consistently practice secure practices.
That is
which is
another
why
thing.
they get caught. Okay.
Yeah.
Now, let's say that you have a computer. They probably will not have OPSEC problems.
Right.
Right. And that is, as far as we know, the number one.
Okay.
Like,
there are certainly some problems with security, and they may be exploitable. Maybe
Yes.
tons of problems.
Okay.
Yeah.
I mean,
do you accept that, like, certainly there are many problems, but there are also things which you can't do very easily?
Yes, I'll agree with that.
Those things might be able to be even harder to do over time, and there might be as more and more things are hacked, there might be a higher propagation of things that are harder to hack.
It's been, I mean, what matters isn't the proportion of things, it's the total amount of computing resources that are available that are still vulnerable, right?
Right.
So if let's say...
That are still vulnerable and are not being vulnerable to other people, for example.
Well, it's arms races for resources.
Yeah.
Exactly.
And there'll be defenders too.
Yeah,
Once you start getting good AI, you can use that to protect your system.
Exactly.
So it's an arms race.
An arms race of computational power.
So security research has been trying for 40 years to figure out how to get humans out of the loop in terms of OPSEC as much as possible. What makes you think that they'll suddenly reverse in the next, 20 years or so? Let's say. Like, people have been trying to figure out a better solution to passwords for forever now, and why has this not happened already? If, considering, what's at stake, I mean,
so there are a lot of
websites run JavaScript.
Okay. We're talking a little bit too much about security. I guess I'd just say, this isn't an end to this by any means, but I guess I'd say there are some things which are automated and don't have humans as part of them, and some things which do, and there are like different endpoints. There are different like techniques for doing a lot of different of these, dealing with a lot of different types of things. I think that like, well, whatever. We're spending too much time on security. But it is not as simple as like, oh, it's just gonna hack everything. It'll be great. Because it does have competitors, and even the things that it's trying to hack have like their own resources. But anyway, okay, so it needs resources, and this quickly becomes a system of economics. If you can't make an AI better than a certain threshold, if you can't make an AI that takes only a very few amount of resources and is better than everything else with it, if you can't make an AI that outclasses everything else, then it has to deal with all the other AI out there that are getting better about as quickly as it is, or that have about the same number of resources. So if there's some efficiency barrier, then if there's some theoretical maximum on the efficiency of intelligence, which is quite possible, and even more likely than not, then how does FOOM happen? How does it take over and beat everything else? Well, it could get a monopoly, but it'll only have that resource, and somebody else will try to create that resource. So it's possible that it could be a little bit better at being intelligent, and then it could like buy out other computing resources. But the amount of time it takes for it to buy that resource and the indication that it has better intelligence is broadcasted through that decision. So it becomes an interesting numbers game, and deals heavily with a kind of power distribution. Yeah.
Consider the following scenario. An AI finds a bug in OpenSSL, and let's say this bug is exploitable in 10% of the computers that are connected to the internet that use OpenSSL. The AI uses this to grab the computing power of all of those things, and it uses that to become more intelligent, and then it breaks all other software, or it devotes at least a portion of that to finding bugs in all the other kinds of software, and probably takes over at least half the internet, let's say.
Right, that would be pretty bad.
Because like it's not competing, because AI is not competing against all of the intelligence of humanity. It's competing against 5 probably unwatched cryptography researchers in a basement. Okay.
Right.
Okay. That's the actual comparison.
Sure.
I feel like as if it's unfair to say, pretend as if all of humanity is focused on security when it's not. And part of the reason is because we don't take security seriously. Period.
Right.
Right. Like.
Okay. But there are certainly other things that you can do with security, like I hesitate to say pull the plug, but yeah, that's a valid thing you can do.
That's like really hard.
Sometimes it's very hard. Yes.
Like
okay. We're not talking about security. Sure. Stop. Okay. So yeah, it does take resources. Maybe it can take those resources. Okay. But maybe it has diminishing returns with respect to creating better AI. Maybe those diminishing returns look like the efficiency barrier of like a theoretical maximum. What if the research on AI is extremely lumpy? What if we have some sudden major improvement that other people don't have? What if the AGI pops up in one spot simply because it's like 10 times better than everything else, and it quickly trades up and gets a strategic advantage? The cool thing is, it looks like we have AGI today in the form of neural networks. I know, a little bit weird that it's my go-to, but it's actually a reasonable algorithm, or well, class of algorithms. It seems to do things that are more and more what we thought were only the realm of what people could do until now. It looks more and more similar. The kinds of things that AIs can do looks more and more similar to the kinds of things that humans can do. I hesitate to say that we have already. No, I don't hesitate to say that we have already created AGI. Like, it's small scale, sure. It doesn't look like a human, okay. It doesn't do the same things, and we don't know how to train it quite correctly yet. But we can train it to do very interesting kinds of things. And if we scale it up, and we're certainly trying to right now, we may see further and further that it becomes able to do the things that humans can do. Yeah, what's up?
So I feel like the sort of thing that we can get neural networks to do is if you have like a well-defined kind of problem and a well-defined kind of set of data, and you know what you're trying to do,
right?
And you can feed in lots of data examples, then it can eventually learn how to like, reproduce a function over like a set of data input, right? But
Yeah.
it seems like what humans can do, like we learn from like a smaller number of examples. And we can learn from a number of different domains. We can do like a lot of things that seem like very qualitatively different
Yeah.
from what the like current neural network paradigms are doing.
Right.
So this
So
seems implausible.
You're saying qualitatively different.
Yeah.
But that implies that no amount of like difference in performance or numbers or resources would allow an AI to become similar in performance to a human. I think that's kind of like
no amount of neural network scaling will make a neural network like a human.
Sure.
But, like, that's not every AI.
Okay.
Yeah. Like when you say that neural networks are example-based, I assume first of all you're talking about a very specific subset of neural network models. You're talking about
Maybe
deep learning, convolutional.
Sure, more like RNN.
Single perceptron neural networks.
Yeah.
Even if you give it infinite nodes.
Yeah.
Maybe infinite, but
That's
if
completely
you give it
understandable.
nodes, it's not.
Yeah, feed-forward neural networks are very limited, shall we say. But some types of neural networks are not very limited. And in fact, there is a recent neural network architecture that has been used to play Atari games, all Atari games, with a certain degree of success.
Do you know like how long it plays? It had to like.
I think it's about 500 games usually. It does get. I mean, it shows you the performance at different scales. Like it shows you what it does at 100 games, 500 games, 1,000 games, 2,000 games.
Is it asymptote?
It seems to asymptote. Yes, it gets to like superhuman performance at like 1,000-ish games, and then it like just gets. It gets like to even more superhuman performance after that, but it gets to different degrees of performance.
It's only superhuman on about half the games.
Yeah, sure. So it's like pretty good, but it's the same architecture as superhuman on half the games. A bunch of different specifications. That's pretty ridiculous.
Yep. This is DeepMind, and they're also applying it to driving games,
yeah.
control things, which are much more relevant to
yeah.
moving robots around the world.
And this is a neural network architecture. Admittedly, a very complex one, but still a neural network architecture. Yeah.
I would just really challenge calling DeepMind an AGI, or even close to an AGI. I watch the videos of it playing games. I'm way impressed. But
yeah, it's certainly small scale. I think that if it were scaled up, and if different techniques that allow for higher scale, bigger and bigger scaled neural nets were introduced to it, that it would gain significantly in performance and surprise you.
Is there any cost to scaling?
Yeah, I mean.
Beyond the dollar value? Like, $5 million doesn't seem like a huge amount of money for Google or something.
Yeah, so.
To produce something that we.
There are entire server farms dedicated, probably even more than $5 million worth of stuff dedicated to like training neural nets in Google right now.
Yeah, this is like the thing where if you have any probability of making a superhuman general AI,
yeah,
then the payoff is going to be so high that the cost almost doesn't matter, right?
Right, except that the cost is still pretty high for at the same scale. like the cost per intellectual performance is still pretty high compared to, say, humans. Admittedly, different tasks, not very comparable in some respects. But if you did make the comparison between the neural nets that are being used and humans, it is currently still pretty expensive. I mean, $5 million for a human brain, effectively, or $2.5 million for a brain. Whereas,
Cheaper than some people's salaries.
sure, it's cheaper than some houses, but it's still pretty expensive, and it's pretty expensive for the performance of just the brain. What's up?
And like, but like having the first one would be like a huge publicity coup. You know, like we've created a human brain.
So
Like, it
yeah,
seems,
that's
you know,
and that's where
even if it's not economical
Yeah.
to like produce output immediately.
And that's where the
It's,
other
you know,
bottleneck arises, the training problem. Neural nets are currently only trained to do some very specific things, like play Atari games. And even though they're pretty good at that, it's not a big enough search space with a bunch of with good enough like heuristics or short-term achievements, tools that it can create that it matters almost yet. So its training is still a bottleneck, but like so is performance. Even if training were solved right now, performance may still be a significant bottleneck. What's up?
Where's the 2.5 million?
We did some napkin math about the amount it costs to have enough RAM to fit a neural network the size of a human brain.
Okay, but it would not be a human brain.
Right.
Right.
But it might be like analogous to one, maybe. Like
But
you might be able to make comparisons.
The EPSL and Henry Markham are trying to make a human brain.
Yeah.
Blue brain.
Blue brain, yeah.
But they're
It's
not-
clearly not the same thing at all. Yeah.
Yeah. Much bigger scale.
Yeah.
And it's going to take.
In order to actually simulate neurons, like
Right. And
you need,
chemistry.
it's more than just, yeah, what's up?
Has anyone in this project ever, thought of going back to analog instead of digital?
So analog is so that you can have scaling values. It's easier to program. I think it's easier to like put together digital projects or to work with digital software, and you can like kind of simulate the analog parts by just having floating point values. So they already kind of did that.
Yeah, okay.
Yeah.
Just
Okay, so yeah. So there's also another thing. I think there's like the AI box experiment, where you have like a super intelligence in a box and talks to you through this text editor or prompt, and it says things to you and you say things to it, and it gets itself out of the box. It's a little unclear how that works.
It tells you your mother is going to die unless you let it out, and then it uses its computational resources to prevent your mother from dying.
Okay.
Yay, everybody wins.
Everybody wins.
You know, Eliezer actually did this.
Yeah.
He got people to pay him $5,000 if they let him out of the box. So tremendous
He
incentive.
lost that one.
He did it 5 times. 2 times they let him out of the box, even though they had to pay him. And he won't say what he told them to get them to let him out of the box.
He sounds like a very convincing guy.
Well, Eliezer.
Yeah.
So this is illustrating a security problem in humans.
Yeah.
Interesting. Yeah. Seems like some people are a little jumpy. So.
An AI in the box in the house. Let me just go get that.
You have an AI in the box?
Yeah.
That's great.
Have a paperclip statue.
But essentially what's going on here is you assume that the intelligence is already so great that it can help you in anything that you do.
That's our paperclip statue.
Yeah. Uh-oh. I'm a little scared now. But yeah, it has near infinite, or actually, I think in this, it's either infinite or near infinite. I think if it was infinite, it would just like immediately win. I guess it would just everything. I'm not sure what infinite intelligence exactly means. I guess AXI to its like theoretical.
No, you just need enough to convince somebody.
Sure, just enough to convince somebody. That's not that hard. Humans are easily convinced.
They are. I mean, if you looked at like the Turing test that's been run,
Exactly.
people are pretty
To
easy to fool.
be able to convince, let's say, 30% of people, there's a decent chance that one of those people will be working on, be in a position to do it.
Yep. So humans are easily convinced, but some humans are less easily convinced. And it seems like you can probably get to the point where it's pretty hard to convince you about things which don't make any sense. But
We have a failure.
okay.
That is how the world ends.
The world is ending right now. This is 2016. Who let the dogs out? Yeah. I'm sorry for all the paper clips.
Far more likely.
Yeah. Whoops. I just forgot. I just accidentally created a super intelligence.
Well, you know, in the 60s, we accidentally dropped 2 live hydrogen bombs in North Carolina.
Wow.
Fortunately, they didn't go off.
Okay.
But that's an example of something that, is sort of equivalent in scariness.
Humans
and we
are
screwed up.
pretty dumb. They must be incapable of even the most basic things.
Wait, it's North Carolina. Let's think about this.
You're confusing North Carolina with Florida.
Anyway, this kind of near perfect information or near perfect intelligence, exceedingly high intelligence, seems infeasible and seems like begging the question, where did it come from? But like, how do you guess people's passwords? Like, they don't give you indication of their passwords. Do you map their existence onto some function for the universe and then compute their password from the universe itself? Doesn't that take a long time? Yeah, it seems like there are a lot of objections to this. It's more of the AI box experiment isn't a real world scenario. It's more of like a thought experiment to show you what a lot of intelligence would look like, for example. But that level of intelligence still seems infeasible. So, what if it develops other technologies like nanobots or solving the protein folding problem? What is the protein folding problem anyway? Why don't you tell me what it is?
Right now, we don't have good simulations of amino acid chains folding up that can predict what the final outcome is, and yet they do. And we don't know how to design proteins yet to take a given shape.
Do we know how evolution designed those proteins?
Well,
They had a lot of time for
a lot of time, a lot of
I mean, they have a lot of time, and they
trial
have
and error.
everything trying.
Everything.
Like, yeah.
Well, except that there's combinatorially many protein structures, and so it really isn't a lot of time in a computational complexity sense, and so it is kind of a mystery how evolution did it.
Yeah. It seems like a pretty complex process, but also requiring a lot of computational resources. Maybe there's a more efficient way to do it, but we're not sure. And deferring the problem of resources to these kinds of things is very hand-wavy. It's saying, well, we don't have that much power right now, but we could potentially have tons of power from this other source that we don't know about. So it's kind of begging the question, is that a valid thing? Is the power...
Yeah, no, I just think the power is going to run out, but there's another thing, which is that I think it's time to split up the groups of
okay.
They are keep continuing.
I'm essentially done, but last points. There's also the possibility that AIs may naturally wirehead themselves. They may realize their own reinforcement loop and then immediately satisfy it and not do anything else, because for at least neuromorphic AI, that's how neuromorphic AI learns, and that's how the software runs. But yeah, maybe for a different AI it would be different. What's up?
Oh no.
Okay, so we're done. In conclusion, oh, I didn't get to one of my points, which was pretty crucial, but whatever. In conclusion, I would like to advise everybody to be very careful about black box terms and like statements about utility or utility in general, and very careful about immediately deferring to like math to examine scenarios that you might find in the real world. AI still looks like it's going to be very important. There's certainly tons of progress in AGI right now. Moore's law seems to be continuing. It's uncertain how far these things. It's hard to predict the future. I mean, yeah. So, any questions? I mean, we're done. Any questions?